We're continuing on our quest to describe motion. We'll now define speed and velocity. What are we learning? We're going to learn what we mean by average speed, average velocity, instantaneous velocity, and we're going to take a look at a position time graph. Our essential question for today is, what are the similarities and differences between speed and velocity? And what is the difference between average and instantaneous velocity? So let's start with average speed. The average speed of an object over a given time interval is a scalar quantity that is the length of the path it travels divided by the total elapsed time. Path length divided by time. The units for speed will be meters per second. So let's write this out symbolically as an equation. Here we have speed equals distance divided by time. Now we like to list these things out so we know what we're talking about. So we'll list out what we mean by S as speed, and we'll give its unit of meters per second. Then we have distance. That's going to be measured in meters. And finally, time in seconds. Let's try this out in an example to see what it may look like. We'll describe the position of the car at two different points of time. Time equals 0, or where we might start our stopwatch, and time equals 30 seconds. Now remember, average speed is the path length divided by the elapsed time. So we want to find the average speed from point A to point B. So our car here is at we've marked this at negative 20 meters. Here's our frame of reference. And at B, it's gone to 40 meters. And it took 30 seconds to do that. When we want to solve this in physics, we always want to start out by rewriting our equation. I know we've written it down a few times here, but we want to keep things very, very organized. So now we're going to do what we call plug and chug, where we've put in our quantities of distance here. The car went 60 meters. How do we know that? It started at negative 20 and went to 40. The difference between those is 60. And then the time interval is 30 seconds. We went from 0 seconds to 30 seconds. So now we divide 60 by 30 and we get 2. Notice that we keep these units here. Meters divided by seconds. Meters divided by seconds. So think about what this means. This is telling us that every 1 second the car goes 2 meters. Now let's see what we mean by velocity. We'll show what we mean by average velocity and instantaneous velocity. First, let's take a look at average velocity. Average velocity is a vector quantity, which means it has a magnitude and a direction. In one-dimensional motion, our direction will either be positive or negative. That's how we'll tell what direction it's going in. We define the average velocity as the displacement divided by the time interval the displacement took place in. Now, the average velocity does not tell us the velocity at any one point in time. It is the average over that entire interval. Now let's expand what we mean by delta x, or change in position. That's going to be the final position minus the initial position. And the same thing with delta t. That's going to be our final time minus our initial time. Now our units for velocity are going to be the same as speed, meters per second. Let's try an example to make sense of velocity. So we want to find the average velocity from point A to point C. Now our initial position again will be here at negative 20 meters. And our final position, again, will be at 40 meters. Now we have another data point here at time equals 10 seconds. And we'll call that point B. Here's our equation for average velocity. We're going to do our what we'll call plug and chug. We have our final position, and then our initial position. And this is our initial position. And then our final time here is 30 seconds. And then our initial time is 0 seconds. You'll see often we'll leave off this initial time because a lot of times we're starting our stopwatch right at, and that will always be 0. Now, we do the calculation and notice that we have a positive number, and we're making sure that we accentuate that. Our velocity, our average velocity, is in the positive direction. Notice that we placed velocity vectors above each one of these points. And in this case, our car is going at a constant velocity throughout this trip. So let's take a look at a position time graph for this motion. Now we've plotted the position x versus the time t. And this is just like what we did in Algebra 1, where we have ordered pairs. At 0 seconds, the car was at negative 20 meters. Notice that we start our graph. Here's our 0. It's negative down here and positive up here. We've also plotted point C at 30 seconds and 40 meters. Now, there's some interesting things we're going to look at with this position time graph. Now, taking a closer look at the position versus time graph for the motion of a car moving along the x-axis at a constant velocity in the positive direction. And in this instance, the graph is a straight line because the car is moving at a constant velocity, which means that it has the same displacement, delta x, occurring in each time interval, delta t. The rise over the run is a slope of a line. Here, the rise is the displacement, and the run is the time interval. Displacement over time is our velocity. We just got through seeing that. So the slope of the position time graph is the velocity. We can see that when we calculate the slope here, we wind up getting the same amount. Let's try calculating average speed and average velocity for an example car trip. In the last video, we calculated the distance and the displacement for a one-dimensional trip in a car. Now we'll set our time intervals to be 10-second time intervals. Let's show our positions at each one of these points. So we calculated our distance from A to B as 22, B to C as 14 meters, C to D as 38 meters, D to E as 37, and E to F as 16. We added all those up and we got 127 meters. Then we calculated the displacement. And here's our displacement vector right here as being negative 83. Remember, distance is a scalar, displacement is a vector, and we're giving our direction here to be negative, and we're showing negative to be to our left. Here we'll calculate the average speed. The speed is the distance divided by the time. We divide 127 divided by 50.0, and we get 25.4. And then we have left over our meters over seconds. So we put in our meters over the seconds. So this is our speed. Our average velocity is the displacement divided by the time. Putting our displacement in, remember it was a negative 83 meters, and then our time, which is the same, 50 seconds. Notice that we get a negative 1.7 meters over seconds. Our average velocity is in the negative direction, even though we were going in the positive for a short amount of times here. Here's a speedometer in a typical car. Note that this isn't a car that was probably sold in the United States because the speedometer is in kilometers per hour, not miles per hour. So if you're on a car trip, you might speed up or slow down because traffic or road conditions. Average speed doesn't give us this information. If you want to know the speed and direction you're driving at a particular instant, you want to use the car's instantaneous velocity. So instantaneous velocity is somewhat similar to average velocity in that it's the displacement over the time interval. The difference is this, that we are going to take this time interval and make it really, 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 really small. That's what we mean by the limit as delta x goes to 0. We're going to make delta x be as small as possible to where it's the instantaneous velocity, the velocity at that moment. If you have a graph of position versus time, the instantaneous velocity is the slope of the tangent line at any given point on the position time graph. All right, let's go over what we've learned so far. First, average speed is distance divided by time. It is a scalar. Average velocity is a vector. It is the displacement over the time. Instantaneous velocity is the same as average velocity, only we're going to make the delta t down here as small as possible. All of these have units of meters per second. The slope of the position time graph of an object's motion shows us the velocity. The velocity is displacement over time. All right, thanks for listening. Complete your Cornell notes, rewind, and review as necessary.